Okay, so we need a new page. That would be done by this, hopefully. And then now we're talking about, what is this, number 13? So in this problem, what we have is a wedge. This is extremely similar to a problem that's number 571, I think, in your guys' lab manual. So now what we have, this wedge has a mass that's 4m, and it's got an angle at the top that's 36.9 degrees. So I'm just going to call that angle theta, and we'll use that as our symbol, and just say over here that theta is equal to 36.9. We'll erase this. And then um, we've got a mass that's sitting on top of this. And we can use the same color for that. That's fine, I guess. So there's the mass right there. So that's a mass m. And this mass is attached with a string. We're gonna use a thinner piece for this right here. And there's also a pulley on this object. So let's actually here. So right here we've got a pulley. And there's another pulley right here. And there's a pulley right here. And there's a rope that wraps around all of them. That goes that way, and then it comes back this way and it attaches here. And then this one comes down and it goes there. That does not look great, but it is what it is. And these two pulleys over here are attached to a wall. Back to the thick pin. So these two pulleys are attached to a wall here, and here they don't move. So that's all fixed. And of course, there's a ground for these things to roll upon. This one attaches basically straight over, so don't ignore this little piece here. And the question is, what's going to happen in the system if this mass moves down, and it fixes for you that the acceleration of this one right here, we're calling that one A. We need to figure out what else is happening in the system. So there's a couple things that you can do first to figure this out. You have to figure out if this one right here moves it at an acceleration that we're calling A. That's the acceleration of the wedge. You have to figure out how fast this one's going to move, like what the acceleration of the mass m is going to be. And what's going to happen is that this mass is going to move down the ramp some distance, okay? Which means it's going to pull cord, right, from this region here. Like this mass has to pull cord, has to make the length of this cord longer, which is going to require that the cord here and the cord here gets shorter. Hopefully that's something you guys can see. Naturally, this mass would go down, and as a result, the cord between here and here gets longer, while the orange cord on the bottom and the orange cord on the top at the same time have to get shorter by exactly the same amount total. But there's two of them, right? So what that means is that this one is going to move down the ramp twice as far as this one moves forwards. I'll stop for a second and see if you guys can understand that. What I would say that means is that this one is going to move downwards with an acceleration that I'm going to call a over 2 relative to the wedge. Why don't you look at it and see if you can understand for yourself, and then I'll explain it again. See if you just start thinking about it for yourself, like spend a minute or so and think about it. Why this one has to move 2 times as far as this one moves. And I think I just messed this up. I messed this up. I'm being confusing. I'm sorry. So this one's A for sure. This one should have been 2A. I don't know why I said 2A. I said 2A and then I wrote A over 2. The The point is that however far this one goes, it has to pull rope from the top and the bottom. So the way you can think about it is that when this moves down by some distance x, this rope right here and here, this rope and this rope have to get shorter by that same distance. So look at it and see if you can convince yourself of that. Were you able to figure it out? I can draw a picture if you want to clarify, but it's you think about it more and it makes more sense. Good. Oop. We have not learned what work is, dude. But yes, if you want to, if that's the way you want to think about it, is not a bad way of thinking about that. I remember you mentioning it the other day, and I haven't really thought about that. If you use work to think about the situation, it does help just a little bit. Okay, now here's the thing about this that's really complicated. All of the accelerations we just talked about are relative accelerations, right? And we learned like last class, I guess, about relative velocities, or we talked about them at least. I don't know if we learned about them, but we talked about them. And when we discussed relative accelerations, we found or relative velocities or whatever, we found that basically, if I know the acceleration of an object block relative to the wedge, in this case it's 2a down the wedge, and I know the acceleration of the wedge relative to the ground, in this case it's a to the right, okay, then if I want to find what this is, if I want to figure out what the acceleration of the block relative to the ground is, I simply need to add these vectors, right? Like this is technically a vector, this is a vector as well, and if I want to find a block ground, then I need to add the vectors together. Because that's basically what our equation says. Like what we can do is we can write the following acceleration equation. We could say a block ground should be equal to a block wedge plus a wedge ground. And we've got those all here, right? So we can find this by combining together this vector and this vector. Does that make sense? Technically, this block is also moving to the right with an acceleration a at the exact same time. It has two accelerations, right? At right angle that are not at right angles to each other. Basically, you've got the acceleration. Whoopsie daisy. So what you've got is the acceleration of one of them goes this way. Here, the acceleration of one of these, which one's a block wedge? 2a is down, so we put this one second. So this vector here, a wedge ground, is a. Maybe use a different color for this. A wedge ground is a, and it goes like that. And a block wedge goes down like this. Oh no, I need to make that much steeper than that. Here, we'll start with this one first. So the acceleration of the block relative to the wedge was down this way, right? At an angle, and it's a length 2a. And a wedge ground is that way, and it's a. And then we've got an angle. Oops, that is not helpful. So then a block ground is going to be that's unfortunate. Shouldn't have drawn that 2A there. Can always fix it, I guess. Basically, we want to go from there. It should be a straight line. I need to get a ruler. It's so hard to draw with this thing. It's okay to write. Like, writing seems okay, but drawing is really hard. I'm sure I could get better at it, though. Yeah, so it's basically a vector that goes from there down to there. Well, that's a lot better. That would be... So this is a block wedge, and this final one would be a block ground. Okay, does that make sense to you guys? So that's the motion, right? That right there is the motion that the blocks... It's not going to go straight down. It's actually going to kind of go off like that. It goes off at an angle. Kind of goes down and to the right at the same time. I'll label all the vectors. Does that help to understand it? This is a wedge ground, a block wedge, a block ground right there. It's the sum of this vector plus this vector, which we have to vector add, right? And we'll show you how we'll do that here in a second. If you guys understand that part, the rest of it is pretty simple, honestly. It's not that simple. It's still a really hard physics problem, but does it make sense to you guys? All right, so let's do some more stuff with this. So the next thing we want to do is to actually like say what this is. But to do that, we really would like to have like a free body diagram so we can understand exactly how we want to write it. So what we're going to do is we're going to draw free body diagrams for each of these objects. Go black again. Okay, so if I want to draw the free body diagram for the mass, then it's going to have forces like this. There's going to be a force going back up the ramp this way that's going to be T. There's going to be its weight, which goes down this way, mg. And then there's going to be a normal force, right, that goes perpendicular like this, and that's going to be n. And then its acceleration is going to be given by this picture over here. The wedge, okay, maybe we use blue for this one just so we have a different color, is going to have forces that look like this. The normal force is going to be pointing back in the opposite direction. That's the normal force between the wedge and the block. There's going to be a normal force from the ground that goes up this way. And then there's going to be a tension, okay? And here's how the tension is going to work. You basically have tension here, that's T. You're going to have tension here, that's another T. And then this one's the one that's weird. Because there's tension in this rope carrying this one up, there also has to be a tension diagonally down this way, okay? So you have T and T. So those are going to be horizontal, so like straight this way. You've got 2T. And in addition, the rope literally pulls down with T on the pulley, and the pulley is attached to the wedge. So you get an additional extra force here, which is perpendicular to N, which is going to go that way. It's kind of down the ramp. This is starting to look really bad at this point, but it's what I can work with for now. And then in addition to that, you're also going to have 4mg going this way. And I believe this is going to be your angle theta, right? Over here. These free body diagrams look horrible. This is what it is, though. Do those forces makes this one's weird. I know that these tensions are weird, but the idea is that this object is being pulled to the right with two different tensions. Like this rope has tension in it, so there's a tension here and a tension here that's dragging the wedge to the right. And yeah, there we go. There's our free body diagram. It's not great, but it is what it is. This is your horizontal here. And I guess if that's theta and this is a right angle, then this one's also theta right here. I think that's all we need to solve it, basically. You guys have any questions? No? So now we need to put these things together. I don't honestly know how I'm gonna do this with this problem because this whole thing is going to be very confusing. We can at least do the equations for this one right here now, though, because what we know is that the acceleration of this one is a to the right. So what we can do is we can write an equation, and maybe we write it right here. And then on the next page, what I'll do is I'll use more room to do this one. So for this picture here, we're going to say this direction is positive x. And if we write down our equations for this, maybe I can kind of erase some of this stuff now and do it up here. So we would write 4ma is equal to the sum of forces in the x direction. In the x direction, you're going to have 2t plus t times the sine of theta minus the normal force pointing back this way times the cosine of theta. Not equal to 0. What am I doing? That's our x equation. And I'm just going to say, for the purposes of brevity, we're going to leave it the way it is and not worry about the y equation. It introduces this new unknown. We don't care about it. There's no friction on any of the surfaces in this problem. So we have that equation. Okay. Now this one is the one that's a lot more complicated. And in order to understand what's going to happen with this one, I kind of want to like clear some space here maybe, or even go on to the next page. So I can maybe try to draw it bigger where it'll be more clear. So we have our, let's draw a line right here. So that's our incline. And then here's our little guy. And we know we have a force that goes this way. Probably should draw it even bigger than that. We have a force that goes down this way. And then we have a force that goes right along the ramp like this. In addition to this, we have these accelerations. And this is the part that I want to try to be as clear with as I possibly can. We said before that the acceleration of the block down the ramp, right, was a, or 2a, sorry. And in addition to that, it also has an acceleration that goes this way. Where since this angle here is theta, this angle would be 90 minus theta right here, right? But in the interest of, let's see, yeah, this is the 90 minus theta, right? So here's what we're going to do. We're going to draw one more line on here. And say we want to make this the positive y direction, and then we want to make this the positive x direction. Okay? If this is theta, this angle right here is going to be theta. Let me move where I've written this right here for now. So we're going to rewrite that one. A is here. This is theta. You can convince yourself that that angle should be theta right there, I hope. And now what we want to do is we want to break up this acceleration here into components because we want to have an x component of acceleration and a y component of acceleration. So we'll do that with, let's say, blue, and say that we want to break up A into components that point this way. That's not thick enough. We need to go back to thicker. Okay. Components that go this way. That was a nice and straight line, first time ever. And this way. Where if this is A and this is theta, then this should be A times the sine. Nope, not sine. This should be A cos theta. And this should be, I'll just put it like this, A sine theta. And then what we say is this: the acceleration in the y direction is going to be equal to this one, and the acceleration in the x direction is going to be 2a plus this. This is almost identical to one of your homework problems in the lab manual in terms of the way you need to set it up and handle it. So I'm going to stop for a second after I finish this next line here. So it's 2a, ax is going to be this vector 2a plus this vector, which is a sine theta. And we might as well finish this off before I stop for a second, which is to say, if I know ay and I know ax, I can write net fx, we'll do y because it's right there, net force in the y direction is going to be equal to the mass of our object, which was m, multiplied by ay, which is a cos theta. You know what? Let's not skip steps. I shouldn't skip steps because it'll confuse you guys. So it's m, and this is a simple step, but whatever. That's that. In the y direction, there's this force, and then there's the component. We could draw in components here as well for this one, right? So you've got this component here for mg, and you've got the component for mg that goes this way. This one's going to be mg times the sine of theta, which the other one's going to be also mg cos theta. So we're going to have basically in the y direction, which points up, you're going to have n minus mg sine theta is equal to may, and ay is right there. It's a cos theta. So there's one equation. And the other equation is going to be net force in the x direction is equal to max. In the x direction, the forces we have are basically this component of the weight, which is going to be mg times the cosine of theta. And then minus the tension force. And that's going to be equal to m times ax, which is this. So it's going to be equal to, I'm going to say ma multiplied by 2 plus the sine of theta. And I will stop for a second now because this is where the physics ends. Those two equations plus this equation right here are all we're going to need to solve for the problem. So this was my horrible picture on this side that I've redrawn here. It's not much better, but hopefully to some extent I've clarified like what it is we're doing here. I know that's all extremely complex. I'm sure you have a lot of questions. Please ask questions if you do. I'll stop for a second. You're all sitting there thinking, none of that made sense. And I thought that I'd done problems with Newton's laws that were hard before until I saw problems like this. That's what you should be thinking right now. Okay, so does anybody have any questions? Koa, are you trying to talk? Or are you just... Oh, okay. Just thinking. Yeah. This one? Just checking. I think it's cos. So the weird thing here, if you go back and look at the problem, is where the angle is labeled. Is that... You see, like, if this was theta, then it would swap them. Does that make more sense? Yeah, normally this vector is the mg cosine vector, I agree. And then this vector would be the mg sine theta vector, but it's just, it's a little different in this case. Does the addition of the accelerations make sense to you guys? What you have to do there? You never see this in 2A, and I really honestly you don't see it at most schools. Most schools do not give you problems where you have accelerations that are not at right angles to each other, or even having two different accelerations in the same problem is really rare. But in physics 1A, we have a bunch of these kind of problems. Okay, so do you guys have any questions about this before we look at the mathematics and try to solve it? Hmm. Okay. No. So one of the things I did here that I didn't explain, and it's important that I do explain it, is I always make it so that the positive direction, okay, corresponds to the direction it's actually going. So while it would be okay to rotate your coordinate systems, no, that would not work. If you make positive x point up this way, or even positive y point up this way, then the acceleration is going to be negative. I don't know if that made any sense. You're perfectly welcome to change this to x and this to y though. Right? Does that make sense? Like this could be x and this could be y, that'd be fine. But both of them have to be positive in these directions. It's almost required. You can also make it so that your coordinate system also could have been. Where'd my pen go? You could have used this coordinate system. It just makes the problem way harder. Like a lot harder. If you use this coordinate system like this way, the normal, so to speak, coordinate system, like x and y, you could do that as well if you want. But this makes it really, really hard to do the problem. I mean, it's already hard enough. It just makes it a little harder. So, yeah. Okay, any other questions you guys have? 2t plus t sine theta. We're going to have to rewrite all these on another page. You think I don't see any tools for like copy paste here. What does that one do? Not what I. Oh, it just gets rid of these things, and then there's just very few options on this. I need to research other software. What's up? OneNote, is that something that's good to use? Uh-huh. Yeah, that would be kind of. The good thing about this is, the one thing that is good about this is I can save all this stuff, I think. And up. Yeah, I understand. I kind of like the boards. It's kind of nice. It's like all this information in one location, but I know what you mean. It would be better if you could do infinite scroll. You just keep going up, down, down, down. Would be good. And this draw. Yeah, right there. Yeah. Let's try this out. Let's see if we copy. I have to be in the program, right? It's not gonna let me. Yeah, okay. So, but I can draw on this. Where's the? Let's see. Do I do a new page or something? Is this the page? Yeah, sure. But like, wait. This is okay. I gotta close that. This is like notes, but it's not drawing space, so I'd have to. No, not that. Sorry, first time I've ever seen this program before. Quick notes, untitled page. Okay. New window. Draw. Yeah, that's right. Good call. Right. Okay, so like here, if I was to, oh, it has a little dot up here. That's kind of cool. So if I was to go up here and, like, for example, rewrite our equations. So we had these three equations. We had n minus and then I don't know if I left enough room for what I want to do on this part. Maybe I did though. Okay, our other equations, I'll just write them more in the middle of the page, are going to be mg cos theta. Those are our two equations there, and then our other equation, which was from over here, was, I'm going to factor this one out a little bit here. So it's basically 2 times no, sorry, undo. It's t. Why do I keep doing that? Each time I push the wrong thing. if we factor a t out of these two, it's going to be 2 plus sine theta minus n cos theta equals 4 ma. Those are our equations, right? I don't know if you guys can tell, but we're trying to solve in this case for the acceleration of the system. I never said that, but that's what we're going to try to solve for, is what the value of the acceleration is. So that's our goal here, is to find what the acceleration is. Isn't that what it says? Yeah, find the acceleration of A with the wedge. So we need to solve these equations. They're kind of complicated. It's not immediately obvious maybe how we solve these. Maybe one of you guys can figure it out. What, do you notice anything that I could do with these equations immediately to maybe eliminate a variable? Yeah. Sure. So we can solve this for n. You can move this to the right. We can plug that in for n. We're not going to do that, though. We're going to find something else to do here. We're going to look on solving this using the elimination method. So I want to do something where I'm going to sum together all of these equations. Okay, and I want to cancel things out. Specifically, I want to eliminate t and I want to eliminate n, right? The rules on how you do this, though, right? Let's see if I can use another color here. Would be, is this going to be like a rainbow? It is. Okay, we'll undo that and just do this. It's interesting. There's not a lot of options here. But that's fine, I guess. Right there. Cool. Thanks. Okay. This for now is probably good. So this is what I'm going to say what we're going to do here. If I want to eliminate the n from this equation, I notice that the n from this equation down here is negative, but it has a cosine theta in it, right? So what we'll do is we'll multiply this entire equation by cos theta. For the second equation, we have t that's negative, and I have t that's multiplied by 2 plus sine theta. So what we're going to do is we're going to multiply this entire equation by 2 plus sine theta. Like that. So what we're going to get is, so n cos theta, right? Cos theta times that. And this one's going to be minus sine theta. That's what we had before. But now it's multiplied by cosine theta. And all of that's going to be equal to ma. But now it's going to be cosine squared theta. This one will get 2 plus sine theta times the whole thing. So what that ends up being is mg cos theta. Okay. We're multiplying 2 plus sine theta times this, so it's times. And then minus t times equals. I lost something here. There was an a here, by the way. I'm sorry. Should have been an a right there. So it's going to be equal to ma times 2 plus sine of theta whole squared, right? Because this times this. And then our last equation stays the same. And now, if I add these equations together, a lot of stuff cancels. So when I add this equations together, basically, can you see that that term cancels with this term? And this entire term here cancels with this entire term here. In addition, that term is going to cancel with that term, right? mg cos theta times sine theta is equal to mg sine theta cos theta. So the entire left side of the equation completely disappears, except for what we're left with now is 2 times mg cos theta equals MA, MA, MA. Every single one of these terms has an MA in it, okay? So it's MA times cosine squared plus this term, which is going to be 4 plus 2 sine theta plus sine squared theta plus 4. Basically, MA times 4 is the last term. MA times cosine squared theta is this term, and then if you expand this out, you're going to get 2 squared, which is 4. You're going to get sine squared theta, that shows up there, and then you get a cross term, which is 2 times the sine of theta. And then all of this, you can probably, those of you that you're probably seeing immediately that you see this cosine squared and a sine squared, right? Those add up to 1, right? So what we end up getting is this. We get 2 mg times the cosine of theta. Oh, we don't even need to write the m's anymore, do we? Let me just undo. Because the m's now cancel on both sides, right? So we end up getting 2g cosine theta divided by, this entire thing is going to become 1. Right? Cos squared plus sine squared is 1. Plus 4 is 9. So 8 plus 1 is 9. And then this term is still there. 9 plus 2 sine theta equals a. And since we know what theta is, then all of this becomes 2g. Cosine of this angle is 4/5. And sine of this angle is 3/5. So whatever all that reduces down to, 8, and then you multiply 5 through the denominator. This will become 6. This will become 45. 45 plus 6 is, God, this is annoying. Let's see. The numerator, 2 times 4 is 8g, divided by 5 times all this, 45 plus 6 would be what? Man, doing math in my head's hard right now. 51? That would be the answer. Where's the eraser tool? Let's see how good this eraser tool is. Oh no! It actually erases things. There's probably different versions of this, right? Stroke eraser, small eraser. Okay, so it was 51. Did I do the math right? 6/5 plus 9 multiplied by 5. Did the math wrong, because it's going to be 5 times 9 plus 6/5. And 5 times this is 45 plus 6 is 51. Okay, yeah, that's the answer. Okay, I'll stop. That was a lot of algebra. But there you go. I lost the pen. So I assume that I can just like scroll down farther from here, Ash. Is that right? Yeah, that's pretty nice. That sounds better. And there's probably some other feature. I can see immediately that there's some features here that we could use. Like we could do things like you were saying, like we can copy. Yeah, I'll probably let you guys answer questions and then stop the recording so this video doesn't get too big. And we'll see how the recording quality came out. But does anyone have any questions about that? There are other ways to go through the algebra. That is probably the one that takes the least number of steps.